We talked about Newman projection for alkanes in the previous videos. Now we are going to look at conformations for cyclic compounds, which we call them cycloalkanes. The smallest cycloalkane that we can form can have 3 carbons, and we call that cyclopropane. So because it's the smallest one, a lot of strains come with forming it. Cyclopropane is very unstable and it's very reactive because of those strains, so it's easy to open the ring up in cyclopropane. Now there are 2 strains in cyclopropane that we need to consider. The first one is angle strain. So if you look at this structure of cyclopropane, the hybridization on this carbon is sp3, and we know that the bond angle for sp3 hybridization is 109.5. However, in the 3-member ring, the bond angle would be 60, which completely deviates from that 109.5 degrees. Therefore, cyclopropane would experience a lot of angle strain. The other strain in cyclopropane is torsional strain, and that happens due to repulsion between electrons that don't share the same atom. So what does that mean? Here is the structure of cyclopropane. So if you look at the cyclopropane sidewise, these 2 carbons are kind of eclipsing one another, and also these CH bonds, the CH bond in the back and in the front, also at the bottom, they are eclipsing one another, and there is no way that this molecule can rotate to release that basically torsional strain. Therefore, cyclopropane is very unstable and experiences a significant torsional strain due to its structure. The next cycloalkane that we can talk about is cyclobutane that has 4 carbons. Cyclobutane can also experience 2 strains, angle strain, again due to the small bond angles, which are smaller than the optimum bond angle for sp3 hybridization. However, the angle strain here is smaller comparing to cyclopropane because we have larger ring. The other strain for cyclobutane is torsional strain, and it is due to eclipsing hydrogens. So if you look at the molecule from this side, these CH bonds, these hydrogens, they are eclipsing one another in opposing carbons. Therefore, the molecule will rotate somewhat this way to release the strain. And this structure right here, we call that puckered conformation. So cyclobutane can basically adopt puckered conformation to release the torsional strain. And to show the puckered conformation on a paper, we draw the CC bonds in a wedge format, which means the CC bonds are coming out of the plane of the page. So these bonds are coming out of the plane of the page. If we imagine there is a plane right here. So this is the puckered conformation for cyclobutane. The next cycloalkane that we can have is a ring with 5 carbons, which we call that cyclopentane. So as we keep adding carbons, we are going to relieve angle strain. The bond angle in cyclopentane is 108, which is pretty close to 109.5, the optimum angle for sp3 hybridization. However, cyclopentane still has a slight torsional strain due to these CH bonds eclipsing in opposing carbons. Therefore, this molecule will rotate somewhat this way to alleviate the torsional strain. And we call this conformation an envelope conformation. So to draw the envelope on a paper, we look at the molecule this way. So these bonds they are coming out of the plane of the page, and we show them with wedge bond on a paper. I also draw the model, actually I took a picture of the model, put it here, and I tried to draw an envelope on top of it. So hopefully you can kind of imagine why we call this conformation an envelope, because it looks like we have unsealed envelope here. The last cycloalkane that we are going to talk about is cyclohexane. This is the only cycloalkane that doesn't show any strains. Somehow cyclohexane can adopt a conformation, and we call that conformation a chair conformation that is completely strain free. So just remember, this is true when we have hydrogens attached to all the carbons. If we have substituent other than hydrogens attached, it would experience some strain. But when we have all hydrogens attached to all of these carbons, it is a strain free in its chair conformation. So cyclohexane can adopt different conformations, and we are going to review them together. The first conformation is the half chair, which is like this. So I didn't attach the hydrogens here because I believe it would be easier for you to follow when I'm switching between the conformations without hydrogens attached. So this one is the half chair. This is the structure of half chair. This is the least stable conformation for cyclohexane. The next conformation is the both conformation, which is like this. Both conformation is more stable than half chair. However, if you imagine there is a group attached to this carbon and there is another group attached here, so there should be some interaction between these groups, which makes it less stable. Both is more stable than half chair, but it is still considered as one of the unstable conformations for the cyclohexane. The next conformation is twist both, which is like this. Okay, so the twist both, these bonds, this one, and this one, they are coming out of the plane of the page, and they are shown here. First, second, and third. And the last conformation, which is the most stable conformation, it is the chair conformation, which is like this. Okay, so if you have your model kit, you can make the chair conformation. The reason that we call that chair is because it looks like a chair. So imagine if this is the sitting area, this is the back of the chair, and this is the place that you put your legs. So it looks like a chair. Chair conformation is the most stable conformations, and we are going to focus on this one from now on in this chapter. This energy diagram shows the relative stability of each conformation. So the half chair is the least stable one. It is the highest in energy. Then we have the both conformation. Then we have twist both, and the most stable one is the chair conformation. So as it is shown in this diagram, these conformations are interconverting to one another at room temperature. However, I can say 99.9% of the time you're going to see cyclohexane as a chair conformation, because this is the most stable one. And this structure right here is the chair flip. We are going to talk about that later on in this chapter. So as I just mentioned, cyclohexane has no strain in a chair conformation. There is no angle strain because the bond angle in cyclohexane in the chair conformation is 120 degrees, which is more than 109.5 for sp3 hybridization. So no angle strain here. It doesn't even have torsional strain because all CH bonds are in the staggered position to one another rather than eclipsing position. I'm gonna draw the Newman projection for the chair conformation in the next slide, so you're gonna have better understanding of these topics. Let's practice drawing a chair conformation. There are a few steps that you need to follow. So overall, we can draw a chair conformation using 3 sets of parallel lines. So I'm gonna draw the first set. So I'm gonna draw them with a little bit of angle. Okay, they are parallel to one another. And then I'm gonna have 2 longer lines and 2 shorter lines. The longer lines are parallel to one another. So this is my longer line, which are parallel. And I'm gonna have shorter lines, which are parallel to one another. So this is how we can draw the chair conformation. I know that might be a little challenging at first, but with a little bit of practice, you'll be able to draw it very easily. Now, on each carbon in cyclohexane, we can have 2 substituents, one axial and one equatorial. We have 6 carbons, therefore we can have 6 axial positions and they are straight up and down. And we can have 6 equatorial positions. And they are at an angle. So let's draw the axial positions first. I'm going to start with this carbon. So as it is clear, and this carbon is kind of pointing towards up, therefore the axial position should be up on this carbon. Then the next carbon, it is kind of pointing down, so the axial position is down on this carbon. So we are going to experience some sort of alternating pattern here. Therefore, on the next carbon, we are going to have axial position going up. On the next one, axial going down, then axial up, and then axial down. Now, to draw the equatorial positions, that could be a little challenging, but for example, if I'm start with this carbon, the equatorial position on this carbon, the bond is parallel to this line here. So this is gonna be the equatorial position on this carbon. And to draw the equatorial position on this carbon, it's gonna be parallel to this line. Okay, I can draw the similar basically equatorial bonds right here on these 2 carbons. So this is parallel to this bond, and this one is parallel to this line. Now to draw the equatorial position on these 2 carbons, we need to draw them in a way towards this shorter tip. Okay, and similar right here. So you are not allowed to draw them to the basically longer tip, so it should be to the shorter tip. So this is the cyclohexane model. As I said, we have 3 sets of parallel lines in this model. So these 2 bonds, they are parallel to one another. These 2 are parallel, and these 2 are parallel lines. Now we have 6 axial and 6 equatorial positions. So we have 1, 2, 3 axials up, and 1, 2, 3 axials down. We also have 6 equatorial positions, so basically they are arranged in the equator of the ring. That's why we call them equatorial. Let's draw a Newman projection for chair conformation. To draw the Newman projection, we need to look through 2 carbons here. So let's number all the carbons in this structure. This is carbon 1, 2, 4, 5, and 6. To draw the Newman projection, we need to basically stand in this position and look through C1, C2, and C5, C4 bonds. So here is the model. The carbon that is marked in red, this is carbon 6. So I marked it. Hopefully it would be easier for you to follow. So this is carbon 6. This is 1, 2, 3, 4, and 5. Now we need to basically stand here at this position and look through these 2 carbons. So I'm gonna rotate the molecule, okay? And we are gonna look through these 2 bonds, C1 and C2 bond, C5 and C4 bonds, and draw the Newman projection. So this is carbon 6, the marked carbon. Therefore, I need to draw 2 circles here. So let's draw 2 circles. This is the first one. And this is the second one. Now, so I need to look through, as I said, C1, C2. So this dot right here is the C1. And look through C5, C4. So this dot is the C5. Now to C2, C1 and C5, we have C6 attached. So carbon 6 is connected to carbon 1 and carbon 5. And looking at this Newman projection, it is coming toward us. So it is in the front. Therefore, I'm gonna draw that this way. Okay. So this is carbon 6. And to carbon 6, I have 2 hydrogens attached. So one of them is basically coming towards me. The other one is going down. So I can show them as wedge and dash. Okay. Now to carbon 2 and carbon 4, I have carbon 3 attached. And it is in the back. So I need to draw it in the back. Therefore, I need to draw a line out of the circle to show the group in the back. So this is going to be carbon 3. And to carbon 3, again, I have 2 hydrogens attached, wedge and dash. Now, we need to look through carbon 1 and carbon 2 bond and draw what we see. So to carbon 1, there is a CH bond going up and CH bond coming to the side. So I'm gonna draw that going up and to the side. So to carbon 1, I have carbon 2 attached. Because it's in the back, I don't show it. And to carbon 2, I have 2 hydrogens attached. One is going to the side upward and the other one is coming down. So since they are in the back, I draw a line or a bond out of the circle. Now to carbon 5, I have CH attached going upward and the hydrogen attached going to the side. So So I'm gonna draw that one connected to carbon 5, which is in the front. And to carbon 5, I have carbon 4 attached, so I don't show this because it's in the back. However, it has CH bonds going to the side and CH coming down. So I'm gonna draw that out of the circle. Okay, so this is how you can draw the Newman projection for chair conformation. If you have your model at home, make the cyclohexane in its chair conformation and try to draw it, visualize it in different orientation.